Section 14.8 on Lagrange multipliers. By the end of this section, you should be able to understand the goals of Lagrange multipliers, be able to explain why Lagrange multipliers work, be able to carry out the method of Lagrange multipliers in a variety of situations. So, before we get into what Lagrange multipliers are, let's talk about the big overall theme here, which is going to be optimizing with a constraint. So last section, section 14.7, this was our first of our two optimization sections here in chapter 14. The goals that we did in section 14.7 was that we were able to classify points as local mins, local maxes, or saddle points. And then we are also able to, determine global mins and maxes on closed bounded region. So the idea here is that, okay, so we have this region here, and we have some function f of x, y, and we want to ask ourselves, what's the biggest that f of x, y can get on this region? That's what we did last section. Now, what we're going to do, we're going to determine mins and maxes subject to a constraint. And this constraint is going to be an equality constraint. Essentially, what we're going to be doing is that for some kind of curve like this, where it's going to be taking, like, for example, the boundary here, what's the biggest or smallest that our function can be on this curve right here. So let's do a warm-up example that will illustrate what's going on here. Find the point on the line 2x plus 3y is equal to 6 that's closest to the origin. Okay, so what is going on here? The line 2x plus 3y is equal to 6. So that's going to, when y is 0, x is 3. When x is 0, y is 2. So here, this is what our line looks like. And so there is some point along this line that is closest to the origin. And it's going to be, just kind of pictorially speaking, it's probably going to be somewhere in there. We don't know exactly where. That's going to be our goal, is to figure out exactly where this is going to go. And so closest to the origin, that means that we're trying to minimize distance. But minimizing distance means that we know our distance formula. We want to minimize the square root of x squared plus y squared. This is distance from a point x, y to the origin, subject to the constraint that our point falls on 2x plus 3y is equal to 6. Let me point out here that there's ever so slightly a difference between this and this. And the difference is, this is talking about finding the point that gives you the closest distance. This is saying find the smallest distance, but those are essentially two different ways to look at the same problem here. Okay, so what do we do? I'm going to show the method that is kind of like what you would know right now before we talk about the fancy schmancy Lagrange multipliers method. You might say, well, we can determine a formula for points on this line. We can say if 2x plus 3y is equal to 6, 3y is equal to 6 minus 2x, or y is equal to 6 minus 2x divided by 3. 2 minus 2/3 x is y. And we can substitute that in up here and say that our goal is to minimize the square root of x squared plus 2 minus 2/3 x quantity squared, where x is allowed to be any real number. Okay, how do we do this? Well, you know, this is the point where it's a somewhat tedious Calc 1 problem. If you take the, this is our function, just say f of x here in Calc 1 land, take the derivative, set it equal to 0, solve for x. The value that you would get for x is going to be, I'm going to skip all the details here. X is 12 over 13. And then check that this does in fact give you a minimum value here. And that's what you would do. And this definitely works, although it's a slightly tedious process to get there. But I will say you can, if you want to try this at home, realize that minimize the distance, if we minimize this quantity here, is the same thing as minimizing this quantity without the square root. The x value that minimizes this and the x value that minimizes this without the square root are the same x value. So minimizing x squared plus 2 minus 2/3 x quantity squared, that will be slightly easier to do computationally. But this problem right here, this is our first example of a problem for optimizing with a constraint. And so let me write here, what are we trying to do? We want to minimize or maximize, one of these two, maybe do both, some function f of xy or f of xyz, depending on whether we're working with 2 or 3 variables. And we would call this, we sometimes call this the objective function. Minimize or maximize f of xy or f of xyz subject to some constraint. And the constraint here is going to be g of xy or g of xyz is equal to 0. Or sometimes if there's a constant over here, we move the constant to the other side. So it can be any constant here. And so we could say this is our constraint. So this is the kind of problem we're dealing with. Minimize or maximize some function subject to some constraint here. So in this case are the f of xy here, f of xy is square root of x squared plus y squared. G of xy is equal to 0. We can write that as 2x plus 3y minus 6 is equal to 0. This is our g of xy. So this is our goal in this section, section 14.8. And so to wrap up the video, let me show us, here is our formal statement of the method of Lagrange multipliers. So suppose that f of xyz, g of xyz, I guess I'm doing this in the case of this case over here. If you just have 2 variables, just cover up the z and everything will go through just the same. Suppose f of xyz and g of xyz are differentiable, and the gradient of g is not equal to the 0 vector when g of xyz is equal to 0. Find the local max and min values of x subject to this constraint. Find the values of x, y, and z and lambda that simultaneously satisfy the gradient of f is equal to lambda times the gradient of g, and our same constraint here, g of x, y, z is equal to 0. And this lambda here, this is what we will call a Lagrange multiplier. So this is going to give us a bunch of equations for us to solve, and so we'll work on solving them. So next video, we'll do some examples, and also in a future video we'll talk about why this works.